Today we are going to answer worksheet number 26. This is from Cambridge International AS and A-Level Physics course book by David Sang et al. So this is the worksheet. Let's go straight ahead. Number 1, you are given with charge Q and you are given with the electric field. So you are going to calculate the electric force. It's simply Q times the E. There you go, you can answer that one. Let's go to number 2. Calculate the magnitude of the electric field. So electric field is equals to the voltage all over the distance. From that equation, your E will be 2.0 times 10 to the 4th power. This is volt per meter. The direction of the electric field, we're going to answer that one, acts towards the negative plate. Let's go to letter B. Describe the electric field between the plates. There will be 2 marks here. The first answer will be the electric field is uniform between the plates. The second answer will be the electric field is at right angles to the plate. Let me draw. I will not draw in the middle, so I won't cover the oil drop. In the edge, it's actually bending. Let's go to letter C. A charged oil droplet of weight is held stationary between the 2 plates. Stationary. So from the word stationary, it means that the Fe balance with the weight. And the weight is given here. First question here, state whether the charge on the droplet is positive or negative. So it is 2 marks. You're going to argue, I'm going to explain, and you're going to answer the explanation. You're going to write the explanation, I mean. Since the droplet is stationary, the electric force on the droplet must be equal and opposite to the weight. The electric force must act upwards, so the charge of the droplet must be negative. So your Fe is up and your Mg is down. Next, determine the charge on the oil droplet. So the charge will be from the formula F is equals to Q times E. Then your Q will be F all over E. We have calculated the E at the top, and the F is balanced with the weight. Then you can get the answer. The answer is around 3.2 times 10 to the minus 19 coulombs. So you would notice that this is just 2 electrons. 1 electron is 1.6 times 10 to the negative 19. So this is 2 electrons. Let's go to number 3. Number 3. Calculate the force experienced by electron traveling the velocity. You have your velocity, magnetic field, flux density. This is your B. And electron. So the charge of the electron E. So electron E is 1.6. We know that. 19 coulomb. Calculate force. Magnetic force is F is equals to Q times the velocity times the magnetic field. Using this, you can get 1.15 times 10 to the negative 13. It's a force, it's Newton. That's it. Let's go to number 4. In number 4, you have the speed, velocity. You have again your B. Alright. So the first one is A. Calculate the force acting. So number 4 is A. Again, you're going to calculate using your magnetic force formula. It's Q times the V times the velocity times the magnetic field. And using this particular formula, you will get 5.12 times 10 to minus 15 Newton. So that is your answer. And letter B, what is Fc? Okay, here, take note that the magnetic force formula provides, okay, Fc. So it means that Fb is equals to Fc. So what is the Fc? Centripetal acceleration. What is the centripetal acceleration of the electron? So let's use the second law. F is equals to ma, then A is equals to F over m. Since the two forces are equal, we can use 5.12 times 10 to negative 15 divided by the mass of the electron. We know the mass of the electron 9.11 times 10 to minus 31. So your acceleration here is around 5.63 times 10 to 15 meter second negative 2. That is your acceleration here. Now let's go to C. Use your answer to B to determine the radius of the circular path described by the electron. So from the circular motion, we know that acceleration is v velocity square all over r. So from here, your r will become v square all over acceleration. The v is given, the acceleration is also given. So all you have to do is to calculate, and you can get 1.14 times 10 to minus 2. This is meter. This is just equal to 1.1 centimeter. So you can imagine how big the circle is using this particular value. Let's go to the next page. That's number 4. Let's go to number 5. So in number 5, let me increase the text so you can see. There you go. In number 5, we have electron traveling into that page, and the magnetic field is into the paper. So using your conventional current, your I is in this direction, opposite to the motion of the electron. And using your code for Fleming's left-hand rule, so this is the code. Code is FBI. So F is the force, B is the magnetic field strength, and I is the direction of the current. Okay? Remember that the direction of current is opposite to the motion of the electron. So FBI means Federal Bureau of Investigation. Again, Federal Bureau of Investigation. You will not forget that. So your force, your magnetic field, and your current. So here, draw the direction of the force experienced by the electron in points A and B. It's very obvious the force is going down because the electron is deflected circularly downward. Remember, it is always at 90 degrees. Here, make sure it's also at 90 degrees. This one. Explain why the electron describes part of the circular path while in the region of the magnetic field. So you are going to explain that one. So I'm just going to give you the explanation. The force on the electron is at 90 degrees to its velocity. That's why the path taken is a circle. That's the answer. Let's go to C. Okay, let's go to C. The radius of curvature of the path of the electron is the magnetic field is 5 centimeter. Calculate the speed v of the electron. So first you need to, since you have 5, we need to have certain arguments here. So here is the argument. The first one is you're going to say that Fb, magnetic force, you're going to say that provides Fc. So since they're equal, the formula of magnetic force Q times velocity times V is equals to mv squared all over r. Okay? You can work it out, eliminate velocity in both sides. Then you can come up with a formula of velocity that is magnetic field times the Q times the radius all over the mass. Okay? So all these values are given in this particular problem. So by doing that, you can have the velocities around 1.76 times 10 to the 7th power meter per second. This is now your velocity here. You can get 5 marks if you're going to show all the details of your calculation. Let's go to D. Explain how your answer to C would change if the electron described in a circular path of radius 2.5. Remember that this radius is 5. Okay? Now your new radius will be 2.5. So it means to say it's reduced to 1/2. Okay? Now, the formula here is V is equals to magnetic field Q times R all over the mass. Now, in this formula, the velocity is directly proportional to the radius. So now the radius is reduced to 1/2. Therefore, the velocity must also reduce to 1/2. So your velocity nu will be velocity all over 2. It's reduced to 1/2. Doing that, it will give us a speed of around 8.8 times 10 raised to 6 meter per second. That's the relationship between the two. Let's go to number 6. Number 6 is here. Right. You are given a kinetic energy of 15,000 electron volt. Remember that 1 electron volt is equal to the magnitude of the charge of the electron. Okay, that is the meaning of 1 electron volt here. The radius is given and the mass of the proton is here. Remember, it's the mass of the proton. Show that the speed, so we're going to calculate that speed. So we need the kinetic energy. Kinetic energy, we are going to solve that first. It's because in terms of electron volt, so it's 15K means 1000 multiplied by 1 eV 1.6 times 10 to the negative 19. It will give us around 2.4 times 10 to the negative 15 joule or joule, depends on how you pronounce it. Okay. Then after that, your kinetic energy, the formula of kinetic energy is equals to mv squared all over 2. Then we can find, you have the value of the kinetic energy, you can find the value of the v. So without showing the details of the calculation, the v would be around 1.68 times 10 to the 6th meter per second. So if you round this off, this particular answer, it is somehow similar to 1.7. Next, let's go to B. This is, by the way, A. Let's go to B. Let me put my answer here for B. So for this proton, calculate the centripetal force. So we know F is equals to mv squared all over r. We know that one. So centripetal force, the mass is there, the velocity is there, the radius is there. So without me writing all the numbers, we have the centripetal force is around 960 times 10 to the negative 14 Newton. That's the answer for letter B. Now for letter C, determine the magnetic flux density. So the flux density is simply the force of the Q times the V and the B. Right? So remember that FB is equals to FC. Okay? So the value of FC will be utilized for FB. So now the formula of the B, the formula of the B will be F all over Q times the velocity. So now you have, actually this is FB is equals to FC, so no problem, you can take the data. Then the B will be around 0.36 Tesla. Okay, let's go to D. So the D here is how long, so it means the time. So we have the formula speed is equals distance over time. Okay, now the distance here referred to is the circle. So the distance is 2 pi r all over s, speed. Okay, all over speed, and the speed here is, we have calculated it, 1.68. That's right, 1.68 times 10 to the 6th power. So distance, this is distance over time, and your time is distance over speed. So this is now time. Okay, so time is distance over speed, and the radius is given. The radius is 5, this is 5 centimeter, change that to meter. So we can actually take the time, calculate the time. It will give us 1.87 times 10 to the negative 7 seconds. That is just 187 times 10 to the negative 9 seconds. Right? Or simply you can say it's 187 nanosecond. Let's go to number 7. All right. Let's plug the battery. It says it's low battery. So let's have number 7. So in number 7, we are going to explain the voltage here. The charger is positive charged ion, so it means this is positive. Take note. So it means our current here, if we're going to use the code here, Fleming's left-hand rule, we know that the force of the magnetic field is going up, so FB is going up, yeah, and it means to say that FE is going down, right? So here, calculate the magnetic flux density of the magnetic field. So you have your electric field because you have the distance and you have the voltage here. Okay, so I think we can answer that one, and it is 6 marks. So let me help you how to get that 6 marks here. So first, let's take a look here. Since the ions emerge away or out of that particular slit here, it means to say that the two forces here cancel each other. The two forces cancel each other, so there is no net force. So here, you're going to argue that no net force acting perpendicular. Remember that the direction of the force is perpendicular to the velocity. You will be given 1 mark for this. Okay? No net force acting perpendicular to the velocity. Right? Now, because you already argued that there is no net force, then you can say now that FE is equals to FB. That's right. It means it's QE is equals to Q times the velocity times the B. You remove the Q. Now you are left with B. So the formula of the B now is electric field all over the velocity here. Now we know the formula of electric field. It's given. It's voltage all over the distance. Then you can calculate the electric field, put it here, and the velocity is given, it's here. So there's no problem with you calculating the B. So without me doing the details of the calculation, the B is around 3.47 times 10 to minus 2 Tesla, right? Or this is just roughly around, if we can round this up, this is around 35 millitesla. Now let's go to B. So for B, I need the space. So let me erase this. Only this. Oops, sorry. Only this. Yeah. All right. No, only this. No. I'm sorry, I need to eliminate this one using eraser. Alright, let's go to B. In letter B, ions from the velocity selector pass into a mass spectrometer. So the ions went into the mass spectrometer, which contains another magnetic field. So a flux density B. The ions all have charge Q, but either have mass 1 or mass 2. So the difference in radius of the two isotopes in magnetic field is given by this equation. When the ions pass through the spectrometer, it means to say that those ions experiences the same magnitude of the B, of course. And the ions all have a charge of Q, and definitely they also have the same V. So these are all constants. Okay? Now from the equation R equals to mv all over bq, yeah, it means to say now that your R, okay, depends on the masses, yeah, because unfortunately these three are constant. So now it means to say that if you have delta R, okay, that will be equal to delta m, so delta r, that will become the delta m multiplied by the constants. Yeah, that's it. So that's why if you're going to explore with this one, delta r means change in r, and then delta m will be m1 minus m2. Yeah, multiplied by the constants. What are the constants? The v over b times the q. Almost done. Let's go to the last page. Let's go to number 8. Show that the time t to complete the orbit is independent. So it's not affected by the speed and the radius. And the formula must be this one. Okay? And it is 5 marks. Let's see how you get the 5 marks here. So let's have number 8. Let's have number 8a. Let's start with the argument. Okay? The argument is again if B provides FC. Okay, you can say provide or gives, it should be provides anyway, FC. Then you can start your calculation here. This is now QVB is equal to mv squared all over r. Now, because of this, you can have the velocity. If you're going to simplify that, velocity will become bq times r all over m. This is your formula. Now, what is t? Now, the t is simply the circumference, the distance, yeah? Circumference of the circle, the distance all over the speed, or v, or d is equals to all over v. Now, the circumference of the circle is 2 pi r, right? And then all over the velocity is bqr over m. So this is bq times r all over m. Okay? That is why your t now will be, you eliminate r, the t now will become 2 pi m all over b times q. And you know that q can be represented by the charge of electrons, so times b times e. So in this formula, you don't see. You're going to conclude that t is independent. This is to get the last mark. T is independent of the v, and the radius of the orbit. That's how you get 5 marks. Let's move on. Let me have some space. No, only this one, only this one. Okay, sorry, I'm going to eliminate this one manually so we can have the last number. Patience. Let's have the last one. Letter B. Explain in words how a faster electron takes the same time to complete the orbit as a slower one. We have the same time, but the other one is fast, the other is slow. It means to say the faster one must travel a longer distance compared to a slower one. So it means to say the other one is moving in a bigger circle, the other one is small. And if they start here, and they will also end here, he will also end here at the same time, right? So it means to say the faster electron must move here, the slower must move here. So you're just going to write in words there. You're going to say that the faster electron, just 1 mark, the faster electron travels in a circle with larger radius. That's all. I hope you can get some ideas from my answers. Thank you. Until next time.